Section 2.3, Zeros of Polynomials in Python. In this section, we'll implement a Python code to find zeros of polynomials, and we'll compare it with a MathTalent code. If you were in an introductory course of numerical analysis, then you can understand the Newton method. The method is formulated in this way. Now, the purpose is now trying to find some point R such that P R equal 0. That is 0 of the polynomial or root of the equation. And now, along with initial the estimate x0, now you can get next better one, updated value, by using this formula. That formula can be interpreted geometrically in this way. There is x-axis, and now there is y core P of x. Then xn, now that is r, which we have to find. Now assume xn is here. Then the updated point can be found in this way. From this point, we are making a tangent line to the point and try to get x-intercept. That intercept is updated to the point xn plus 1. Again, along with that point, you are going over there and curve and try to make a tangent line and try to get x-intercept to get xn plus 2. So the method is converging very fast. However, you have to provide the derivative value. It is a little bit cumbersome, but you can get the derivative value by using the harness method very effectively. Let's see how can we get derivative value. The remainder theorem says this one, the polynomial is divided by x minus n, then there must be a quotient 1 degree lower than that of p, and plus pxn, this is constant. Now if you differentiate this equation, then left hand side is p prime, and right hand side by using product rule, and first one is qx, and x minus xn, and q prime x, and this is constant, so this will disappear. Now, so no matter what it is, and once it is not blowing up, of course polynomial is not blowing up in finite interval. So yeah, if x is xn, then this is 0, and no matter what it is, this will be 0. So here we reach at p prime xn is qxn. So it looks like we have to evaluate the value at xn for p and for the quotient. Then you can make this ratio and update the point. This can be implemented very effectively, efficiently, along with the harness method. And in high school, it is called synthetic division. Okay. For example, p of x is given in this way, and we want to use Newton method and harness method to find the approximate zeros of p near 3. Okay, here we import numpy, and coefficients are collected, 1, -4, 7, -5, -2. And now NumPy method is poly 1D along with the coefficient, then there's P. Okay, so once you print up P, then you can see that one, the same as this one. Now, by using poly dr command, you can find the derivative. So you can see here now derivative, and there's printout, so you can see here. Now you can find roots by using root command for P. You can find it. You can see here now 2. There is imaginary unit. Now 0 means that this is a real solution, and we have another real solution, and there are 2 complex conjugate solutions. And here P3 and P derivative P prime 3 are printed out, 39 and 19 and 37. Okay, this is when you are using built-in functions, then you can handle it. But here we'll implement the code for Newton-Hana method to find the approximate 0 of P near 3. Okay, in Python, okay, we define Hana along with A. Now argument is A and x0. And for given point, we try to make the function value, the polynomial value, and derivative value. And coefficients are given in this way from an to a0. That means that, like over there, decreasing order, and 1, -4, 7, -5, -2, that is now the collection of coefficients. And here, for this one, now this portion is computing now the function value, P at x0, and now there is P prime at x0. So we'll not go to the detail, but this is Hono's method to get here the polynomial value and polynomial derivative value, and applying twice of Hono's algorithm. In high school, you learned it with the name synthetic division. Okay, and now here, by using Hono method, here Newton iteration can be organized in this way. Some x0 is given, now it save into x, and then now here call Hono along with the coefficient and x, and here now the function value and derivative value will come out, and minus the ratio is correction term is now added. Once correction term is in modulus bounded by tolerance, then we break the iteration. Okay, that's 2 functions, and now we call in this way, we collect coefficient, and x0 is 3, near around the 3, we want to find the 0, and tolerance is 10 to the minus 12, and you can write this one for instance, rather than this way, you can write this one here, 1 e to the minus 12. You can write in this way. But anyway, it's okay. In fact, in Python term is 1 e minus 12. You can write in this way. Then it's 10 to the minus 12, and maximum possible iteration is 1000, along with the setting we call Newton-Horner. That function is called. This function we use Horner like that. Now, then the output is the limit value, converting approximate value and number of iteration, so that we try to print out here x0, 3, now x, the output over there, and number of iteration. So the result is now here x0 is 3, x equal 2 in 7 iterations. We give large enough maximum iteration, but it converted in 7 iterations. The above Python code must be compared with the following MathTalent code. Here in MathTalent, the difference is almost the same. Here the difference is rather than AN to A0, now we are using here opposite way. And also I want to show you that once it is from A0, the order is given, then how the code is organized there. And this portion, you can see quite easily, this portion is really almost the same as that now. The difference is that once you try to access that array A, then in MATLAB, the index starts from 1. In Python, index starts from 0. That is a major difference. Now, this Newton-Horner in MATLAB is also, if you try to compare with the Python code, then is really almost the same. Yeah. And now, in separate file, we call Newton-Horner. The separate file name is given here. Now, A is defined in this way. Now, there's A0 and opposite way, save the x0 to 3. And here, tolerance is 10 to the minus 12. And it makes 1000 the same. Now, we call Newton-Horner along with the variables. And then, now output is xn, the iteration count, and we print out, then output is now here x03, x2 in 7 iterations. Exactly the same result can be obtained. Here we have observed that Python programming is as easy and simple as MATLAB programming. Particularly, NumPy is developed for MATLAB-like implementation and with enhanced convenience. And NumPy is the background for SciPy. And also, Scikit-learn is using NumPy so that NumPy will be used very extensively, and that NumPy is quite similar to MATLAB implementation. Okay, and Python uses also classes and here open source programming language. That explains why Python is fastest growing in use, so that sooner or later Python will dominate the programming. Okay, that's the end of the section. Thank you.